Okay, thank you very much, Paul, for a very illuminating talk, a very nice walk through the Devonian. Setting up now for our next, we'll move straight on to our next talk speaker, who is Dr. Christopher Cleal from Bristol University, who's going to be talking about, is this the Forest Primeval? Life and times in the late Carboniferous swamp forests. So Chris, straight over to you.
Right, let's get this
Very much.
technical stuff organized. Well, we've seen that forests have really started to develop properly in the early Carboniferous. We know them from large areas of the world, particularly in tropical latitudes. Is the controller? So, which is the? Yeah, for the slide. Oh. Oh, yes. But by the end of the early Carboniferous, things were starting to change. We know that because we start seeing large quantities of coal appearing in the fossil record. Now, obviously, we have studied coal over a couple of centuries because of its importance as a fuel resource. And we know now that it is clearly just fossilized peat. We know it from a variety of sources of information. The most obvious is these calcite nodules you get in certain coals. And the calcite forms early on in the formation of the peat deposit and impregnates the plant tissue before it decays significantly or is compressed and preserves the tissue of the plant in remarkable detail. You can see here there's various cell structures preserved, leaves and stems. Even the one bottom right is a fern pinnule, where you can see the lamina of the pinnule and two groups of sporangia on either side of the midvein. So why are we getting this sudden increase in the buildup of peat, particularly in the tropical latitudes of the time? To understand this, we need to go back to look at what the world was like during the late Paleozoic. In the early Devonian, which is when Paul was talking about plants were starting to have a significant impact on the terrestrial environments, there were two main continental masses. There was a southern Gondwana mass and a tropical Euramerica mass. And as you go through the Devonian, those two land masses come together, mainly through the northward drift of Gondwana. And when you get to the early Carboniferous, you end up with one large mass, more or less one large mass known as Pangaea. And in the tropical latitude, you can see the pale blue, which is large areas of continental shelf. This is where shallow marine environments were widely spread across the environment, the tropical environment. But then when you go further yet towards the end of the early Carboniferous, about 330 million years, 323 million years ago, large areas of ice started to form in the Gondwana landmass. Now, Paul was saying that the late Paleozoic Ice Age, in fact, started rather earlier in the Devonian, but it was rather patchy. It didn't have quite the extent that it did by the time we get to the middle Carboniferous. This extensive ice sheet caused a significant fall in sea levels. And that resulted in large parts of what had been continental shelf in the tropical latitudes to become exposed coastal plains on which plants could develop and swamp environments developed. This is one of the earliest examples of this coal swamp environment. I've been working on this with Christine Strulu-Derrien in Angers and Alan Spencer in Imperial. It's stuff, the deposits are stuff full of plant fossils. We can interpret the plant fossils, and this is our take on the environment. Basically, a muddy coastal plain covered in plants, sometimes dense enough to allow peat to develop, and then you get the coals. These swampy environments are fairly patchy at this time. They're widely spread over the one in northern France, but we have in southern Scotland in the limestone coal group. You get them down in the Balkans and the upper Silesia, and also in the Appalachians, although that flora hasn't been described properly yet. So this is really the start of this unusual type of peat-generating habitat. When you get further into the early part of the late Carboniferous, it's about 315 million years ago, the ice cap has expanded even further reducing the sea levels, falling sea levels. And this has resulted in an even larger area for these swamp biota to spread. And at the start of middle Ashkirian times, we can pretty well trace it as a more or less continuous belt of swamp stretching from the Appalachians and the Great Lakes in America across the Canadian Maritimes, much of Europe, down into the Balkans of northern Turkey and into the Donets. This covers an area we estimate at about 1 million square kilometers. The environment was comparable in some ways to what we saw in the Serpent that we saw in northeastern France, northwestern France. But the areas where the coal swamp, the peats were developing was more extensive. This is why we get much more coal deposits, much thicker coal deposits, spread right across, as I say, from the eastern North America right through to the Asia Minor. I haven't got time, obviously, to discuss in any sort of detail any of the major groups of plants. I'll just touch on a couple of the more iconic groups. The Lycopsids, the club mosses, which again Paul was discussing briefly earlier. These were probably the most important in terms of biomass, certainly for the first perhaps 5 to 10 million years of the swamps. They were curious plants, to say the least. They are usually reproduced like the one in the middle, like a tree with a top knot. But in fact, that was not the normal form of the plant during most of its life. They had a determinate growth. They would grow very rapidly. These were perhaps up to 30 meters tall. They would grow to their full size before putting the crown on from which the cones are produced, and they would reproduce. It's then thought the plant would then die. This also seems to have occurred very quickly. From what we can make out from the anatomy of the trunks, it was mostly not wood. There was a central core of wood in the center, but the bulk of the thickness of the trunk was made of cortical tissue, and this allowed the plant to grow very quickly. It's been estimated that they could grow to their full height, full stature, in perhaps as little as 25 to 30 years. I like to think of these perhaps as the James Dean of the plant world. They did fast and died young. But it also meant that they were producing vast quantities of peat, and which is why we have this significant buildup of peat from the late Carboniferous onwards. These are the sorts of fossils we know about them, and we can determine a great deal of information about the anatomy and the morphology of the plant. Occasionally, you also get them preserved as trunks in situ. These are ones we found up in North Wales, a place called Primeaval. You can see on the top, the upper picture showing 2 trunks which are embedded in a coal. Clearly, these plants are growing in a peat substrate environment. They started to grow up to, they obviously grew to a fairly substantial size given the width of the trunk, but then it was flooded by water and sediment which killed the tree and allowed the cast of the bottom part of the trunk to be preserved. The one on the right has been excavated out, and if you happen to be in Cardiff, the National Museum of Wales, you'll find that on display now in their fossil swamp gallery. Another iconic group of plants that we do find in these deposits are fronds like this. This was for a long time known as the age of ferns because they're probably the commonest and most easily identified type of fossil found until the early years of the 20th century when it was found out that most of these weren't in fact ferns. They were seed plants, some possibly distantly related to cycads, other ones are very primitive forms with really very difficult to relate them to any modern day taxa. they could vary from scrambling plants to trees. You do get the seeds occasionally. The one bottom left-hand image is Trigonocarpus, which is from one of the Medulazalian trees. These were plants, unlike the Medulazalian, unlike the Lycopsids, which favored the swampier, the peat substrates. These probably favored more slightly drier habitats within the swamp, levées, and other sandy substrates. We know quite a lot about these plants now because of the extensive fossil record. They've been studied for 200 years. And the botany is fairly well understood. It's also been understood that the distribution of the swamps hasn't been constant. We know that they could potentially extend from North America right through to Asia Minor, but not all the time, everywhere. And so a few years ago, my colleague Barry Thomas and I thought it would be fun to just actually try and document exactly how the distribution of the coal swamps varied through time. This was in the early noughties, high-tech time. We did it a really fancy way. We got photocopies of paleographical maps and drew on them where we thought the coal swamps grew, and then just gridded it and counted up the squares. It sort of worked. I'm sure somebody could do it in a fancier way today, but I think the basic model works. When we did this for a whole series of maps through the Carboniferous and Permian times, we came out with this sort of pattern. You can see that the forests broadly break down into two sets. You get the ones in Europe and North America in the earlier part, in Bashkirian times and Moscovian, and then you get the Chinese Caucasian floras, which replace them developed slightly later in the Permian. When we compare that with what was then known about the distribution of the Gondwana ice cap, this was based on work by Gonzalez in Argentina. There's been more recent work by Chris Fielding in Australia, which basically gives the same story, that you have a series of glacial and interglacial periods, but with one significant interglacial period in Casimovian Gazalian times, as it's known. We also compared it with data from Siberia. There was no polar ice cap in the north at this time because there was no land. It was just ocean. But in the mid-latitudes in Siberia at the time, there is vegetation, and two famous Russian paleobotanists, Sergei Mayan and Marina Duranty, concluded from the distribution of the plants that there were two cooling periods and one warmer period. And when you compare them, clearly there is a correlation between the patterns that you see. Now, one thing, of course, we always taught at school, you don't confuse correlation with causation. And the big debate has been, is this coincidental, or did the climate change cause the forest to collapse? Or did the contraction of the forest perhaps cause climate change through changing the carbon budget? The debate is still going on. I don't think there's a definite answer to it yet. But one of the things we've been trying to do is, at least within the European and North American forests, is to get a better handle on the dynamics, the species dynamics, the vegetation dynamics that we can see. We have a whole series of coal fields where we can determine patterns of species diversity. This is some work I coordinated on a UNESCO-funded project a few years ago, where we took specialists from some of the coal fields in Europe and North America, and asked them to determine patterns of species diversity. The different colors of different plant groups. I should have put that under the caption, I'm sorry. But the blacks are the Lycopsids, the blues are the calamated Synopsids, the reds are one of the seed fern groups. You can see that there are similarities in some of the patterns. One of the things you notice in the lower Duckmantian stage is a peak in diversity in at least 3 of those curves. But there are also differences, and one of the things we're trying to do is what are those differences meaning? We're still doing some of this work. This is literally hot off the press. This came out, I think, about 2.5 weeks ago. It's work done in Nord-Pas-de-Calais in northeastern France. And again, you're seeing effectively a unimodal curve, which is typical for the Euro-American floras, but with a series of interesting increases and decreases in diversity. The aim is to try and look at these changes in diversity as to how this can be related to the physical environment at the time. There is climate change occurring at this time, but this is also a very tectonically dynamic environment. The two continents that have come together to produce these lowlands were continuing to push. We were getting a mountain range at the just to the south of here, the Central Pangaean Mountains. This was causing disruption to the landscape. It was causing changes to the sedimentation patterns. And so what we've been trying to do is to relate the vegetation change to these changes in the physical environment. This was a chart which was done as part of the UNESCO project. It's basically the work of Stan Prusztal in Prague and Arthur Kedzior in Krakow. And it shows the gradual change from essentially marine, the blues at the bottom, going through up time to more terrestrial, where more plastic sediments are washing in, and eventually where the reds and the browns are is where substrates are becoming drier. How does this all relate to the changes in vegetation we see? Can you relate any of the changes in diversity to these changes in the physical environment? At the moment, it seems yes, we can, but not all of them. Some of the changes in the vegetation do seem to be cross-cutting between basins and may actually have a climatic, reflecting a climatic signal, but I think that's an exception. Of course, at the top, at the end of the Carboniferous, coals have pretty well disappeared from Europe and North America, and we start getting the Chinese coals coming in. I'm not going to talk about those. I think Jason probably will be talking about that this afternoon. But it's part of the relationship between these two biomes is quite interesting. Jason and I did look at this a few years ago, how you can explain this apparent migration of a biome over thousands of kilometers, with no apparent or very limited evidence for any land bridge. There may be one, but that's still, I think, to be confirmed. So this is the Forest Primeval. This is my Forest Primeval. It's not the earliest forest, as Paul has shown, but I think it's probably one of the most important forests in the Paleozoic, at least. It's the first time we have reasonable evidence of a large-scale, continental-scale forest, which may be having a global impact on the environment and climate. Thank you.
Okay. Thank you, Chris, for a really nice and well illuminated talk about our Carboniferous time period. And we're now going to move on to our next speaker, who is Estrella Luna Diaz, who's going to be talking to us about understanding memory of fossil trees to environmental stresses. And it's rather different and something I've been looking forward to since reading the program. So Stella, over to you.
Thank you. Everyone can hear me. Good. Thank you for inviting me to give this presentation. My name is Estrella Luna Diaz. I'm a plant pathologist at the University of Birmingham. And I realized that actually this talk can be a bit different to what we have just here. We are not going to be talking about millions of years ago or hundreds of years ago. We are going to be talking about what's happening to the trees now and how they are acquiring memory of stress for the future. So this is all part of a really large project that is called MEMBRA. And this is funded by the Future of UK Treescapes. This was a special call that was a few years ago, a strategy to actually increase the amount of woodlands that we have in the UK. So what does MEMBRA mean? MEMBRA stands for Understanding Memory of UK